the first method is only applicable to and overdamped system. Okay, so for example, this method we still consider is our GS. Okay, so this is an open loop system. The open loop system have the characteristic something like this. So this is time. So if we draw the unit step input response of G. Okay, so this GS is our open loop system. If we draw the unit step response, that is the system we're dealing with for the first approach. And in our textbook, the textbook mentioned this one is called the S-shape curve. S-shape curve basically saying for this S-shape, they exist reflection point. Reflection, that means the curvature change from positive to negative or vice versa. That's the reflection. But in terms of our dynamics, simply it's indicating this is an overdamped system. Okay, only have an overdamped system. The damping ratio greater than or equal to 1 have such features. Okay, so basically here is the overdamped systems. That means so the first approach is only applied to the overdamped system, the open loop systems. Okay, so say we don't like such a system because it's damped too much, which means the response too slow. We wish the system can be a little bit more. We wish can we change something and quicker. Okay, so that is this design thinking. So for this method, we need to start with the preparations. So now for this one, say our design goal is to have a controllers. Hopefully this controller GC, and again the GC is the PID controllers, or combined of the PI, PID, whatever you. Okay, so that one we combine in this way. We wish to achieve is positive, negative. We wish we can modify the transient response. Okay, that is the goal. And again, for this overdamped, we think in our original evaluation, the system is too slow. Okay, so under these situations and this approach, this suggested is this. Values for type of the controllers, and we suggest the KP value and TI and TD. Okay, so the same thing, we have a PID and PI and P controller D. Well, I don't know why. So for this one, again, that's suggested value based upon two parameters. From here, if you are able to identify the reflection point, okay, then from the reflection point, you simply draw the tangent. Okay, you draw the tangent line. So let me do it carefully. So this is tangent to the reflections point. Okay. Tangent at, okay, tangent to the curve at the reflection point. Okay, you know what I mean. Okay, basically, at the reflection point, you draw the tangent to this the S-shaped curve, and So from here, you should be able to identify, okay, this is one intersection with one and another intersection with here. So here you'll be able to allow you to identify two parameters here. And here, in terms of our textbook, we define this period called this duration called T, this duration called L. Okay, you need to identify the two parameters first, and then here this is a successive value here. Kp will be equal to 1.2 T over L and 2L and L over 2. And this is 0.9 L over 0.3 and 0 and T over L 0, 0. Okay, so for this method, it's critically you need to determine L and T. And for such a system, if we have identified the L and T, so that means the system can usually describe by exponent of minus Ls and Ts plus 1. We can verify this, but let me skip off this, okay? And so basically L and T corresponding, we have a system like this. Furthermore, if you want to generalize the systems, the description of the systems, and you might wish is you can scale it up. So for example, you can say I multiply with any constant gain k. So under this situation, then corresponding is a k. So basically, you can allow yourself to scale the magnitude of this one by monitoring, revising the value of the k. Okay, so that is a general description. So that is a theory, and again, in a few minutes, I'm going to use MATLAB to demonstrate how this design be looking like. Okay. Before doing that, as engineers, do you have any questions to this method? No? You are happy about this? Okay, if you are happy, then I will give you a very quick test. So say if I provide you a system curve and any S-curve, S-shaped curve, okay? I present it to you and say that is the identifications of the system's dynamics. And apply this method to identify, at least I ask you to identify the L and T. Then with the curve presenting to yourself, okay, so that is a curve. Something like this, that's it. Okay, and this is time. Then probably you're going to face the first challenge. Where is the reflection point? Right? Where it is. Someone say, oh, looks like here. Someone looks like, oh, that's here. The determination of the reflection point is going to change the value of the L and T a lot. So that is the first challenge, and that is a very practical engineering challenge. Right? We talk about this theory. I've done my job. Remaining this one will be yours. This is a very practical issue. Okay, and usually I can tell you the L and T, this one usually is belonging to the technique we call the system identifications, and hopefully in your instrumentations you have learned something about this called the system ID. Yes.
Yeah, I had a question about T. Does T measure
from the intersection here to here?
Okay, it measures to L.
Yeah. And L is from 0 to intersection. Basically, when you draw the tangent line here, intersect with this axis and intersect with the one value here. So that is a measurement. Okay. So back to this issue, usually the L and T are belonging to the topics about the system identification, system ID. And usually, when I learn these things, I learn this kind of techniques, the system ID from instrumentation-related classes. So from there, hopefully, you can dig out the kind of the the method or any techniques you learn from there. And that will help you to better estimate the starting point for the reflection point there. Okay. And so that is a point I kind of point out to you. So when I this morning prepared these lectures, our textbook didn't say anything about how to determine this point, or even didn't say how to get the value, two values, but just assume we are given the two values, then we proceed. Okay. So that is the point I bring to you. Okay. Now I'm going to use one example and to demonstrate this. Again, this first approach is only applied to the overdamped system. If your system is not like this, if your system doesn't have like this, then basically the first approach won't apply. So now there's quite a few issues with the first approach, but I think the first approach is very interesting. So say we consider, I just give to you L equal to 1, L equal to 0.2, we are given, and T equal to 1. Okay, so that's a given one. So basically we try to unify our learning by doing this. And so for this case, basically we applied our rules, and basically our G we're dealing with exponent minus 0.2 s and s plus 1. Okay, so basically that is E minus LS and TS plus 1. Okay, so that is a one. So that is the system, open loop system we're dealing with. So for this case, we consider this is our open loop system, and we combine with our controllers. Like this. Okay. So now controllers, GC will be equal to KP 1 plus EI. So now again, our goal is to design PID controllers, and per the Zeilger-Nichols first method. Again, we simply exercise, and I haven't assigned the design criteria yet, but if we want to do it, we can do it. Okay, but here we simply exercise this method. So now with this one, we measured, or this one given, so here we can say the KP will be equal to 1.2 T over L, and that is equal to 6, and TI equal to 2L, and that's equal to 0.4. TD equal to L over 2, and that is 0.1. Okay. So that is our design systems. Then we can compare their time response and to unit step input response, and of the original and the control. We see what happens. At this moment, probably you can begin to imagine how you can implement this one. Okay, so right now I'm trying to implement the first method. The first method, okay, and using this as one example, okay, and so here L equals to 0.2 and T equal to 1, okay, and the first one I want to draw the open loop system. Okay, so without controllers, I want to do the open loop system, and we can try to do it. Where is the open loop system? Is this one, right? Again, I'm going to use the step command. Usually the step command is the system. The system we run is transfer functions of numerators and denominators, right? Something like this one. We have a system like this. How do you do it? Here the denominator is okay. We know how to do it. But numerator is in such a weird form. We haven't learned this before, right? And yeah, this morning when the textbook didn't provide any example to the first approach. I know why. Probably is this the reason. This morning when I come here, I said, "Oh, holy cow! How can I do it?" I found a way to do it. I should be proud of myself. Okay, so here to input your system, to describe your system in a general way, and that is the way to do it. For example, the systems of the open loop system, and for example, let me directly write it up like this. EXP minus 2 minus L, L times minus L times S, okay? S is the lowercase. And divided by the denominator is TS plus 1, T times S plus 1. And here T and L has been given there. And to doing so, and hopefully the step is the step functions, and what I want to try is system. Oh, okay. So hopefully this will be working. And however, the system won't recognize, if you only type this, the MATLAB won't recognize what you are doing here. Okay? And he wouldn't know what is S. So here you need to add one more thing, and this will be your take-home information. You simply you define your S parameter using here as using this command. TF. This is provided by MATLAB. Don't ask me why. That's the syntax. Just use it. In this way, after this end of this line, you simply declare as is the one we're going to use for describing such a function. Okay, so after doing this, then you should be fine. Then we see what happens. So let me save it and withdraw it. So let me turn off this. 1, where is 1? Oh, 1. Is that right? L?
Your L is lowercase in your open system.
Oh. Thank you. Okay, so that is a 1, and let me try to extend it. So say from 0 to 0.01 to say, right now it's simulating to 6 seconds. Let me say go to 15. Okay, so that is the system. Right now you can see the system here look like, here we think we have an L shape. But again, that is the point I mentioned from here. If I present this curve to you, it's very, very hard to identify the reflection. Okay, usually if the curve is symmetric, basically reflection will be right in the middle. But here, at least for myself, my bare eyes, I couldn't identify exactly. So that could be the uncertainties, the resources of uncertainties here. But anyhow, we proceed. So right now, I'm going to implement the closed loop system. So the closed loop system, C over R will be equal to GC times G1 plus GCG. Okay, so we plug in GC into here, and basically that one will be equal to you simply plug in the GC and as G into here, and you implement the whole thing. Okay, that will take a few minutes to write it down by hand, and then we implement it into MATLAB, and that one will be here. The system closed loop system, and again that will be equal to Kp and multiplied with exponent minus L times S. I have implemented, so let me right away to write down the things. And Pi times S these are numerators and denominators. Okay, so here I simply copy the information numerator here. So because here we have used this kind of special command, so here you can do it like this. If you don't want to type this whole thing again, you simply just use this one. Okay, so now we have system closed loop equal to C divided by E and C. Okay, so the step. Let me copy this one. Closed loop, and let me hold on. Okay, so we see what happens. Let me double check. Kp exponent minus Ls multiplied PIS plus 1 and PS squared PI PS squared plus PIS. Okay, good. Oops, some mistake here. I think there's a mistake in my typing here. Let me double check. Oh, I haven't. Kp, I haven't input this value yet. 1.2 multiplied with L divided by okay, so let me do this again. Okay, so here is a comparison of our original and revised version. Okay, and again, this one in our revised system still have the too big overshoot. So from here, you can just, if you don't like it, you can just randomly. So here you can modify, just randomly say equal to 2L, see what happens. Let me do this one quickly here. So here's 2L. Oh. Not good. L divided by 0.55. Okay, so that is the one, and you can keep playing. So say L equal to say anything you name it. Okay, so that basically here I show you running all the time. So basically that's the way, and we can keep playing about this one. Okay, so that is the one, and we can stop.